In this video, I will continue to model the air friction for objects thrown up in the air, where the air friction is, making some changes to the trajectory. And today, we are going to analyze the motion of badminton. So that is going to be a motion in two dimension. We know that for objects that are moving in air, they are following this parabolic trajectories, okay? But we will see that for objects which are, for objects that the air friction is important in their motion because of the geometrical shape of the object, like a badminton, or like if the object's mass is lightweight and the object's surface area in the air is large. In that case, there's going to be this fluid force on the object, saying that the fluid is got, we can model the air as a fluid. I mean, in terms of physical terms, that the air is the motion of any object up in the air is just a fluid motion. Okay, so we analyzed in the previous video the motion of like an object like the coffee cup filter, which is very lightweight, and we know that the coffee cup has a very large surface area because the paper is open, etc. So that we have modeled, and we have modeled the frictional force as the force which depends on the velocity, okay, which is proportional to velocity, let's say k1 times v, and also which is proportional to velocity square. Okay, there are two types of air friction up in the air. One is linearly dependent on the velocity, and the other is depending the square of the velocity. And in the most general case, any object up in the air, the force of friction is going to be like minus kv plus again k 1v k2v square. Where k1 and k2 are just some parameters. They are coefficients of these frictions. Why do we have such a dependence? Well, for objects which are relatively moving slow, and also geometrically they are not occupying much volume in the air, this term is dominating. But for objects which are which have large surface areas, or the objects which are moving faster, this term will dominate the air friction. Well, in most general case, of course, you can always put your frictional force in this form, and then by just appropriately adjusting k1 and k2 parameters or coefficients, you can model the air friction. Anyway, for badminton, since the motion starts relatively at high speeds, and also the badminton has some surface area, for this video we are going to I'm going to model the air friction, to be minus k times v square. Okay, the badminton starts its motion with high velocity. This happens when the player just hits the badminton ball with its racket at like high velocity. And also, since the badminton has this shape, where moving against air, it has some surface area, right? Because of this, and I'm just going to model that air friction to be in this form, where k is the only one coefficient of friction, and v square is the velocity square up in the air. There is one thing over here is that this is the magnitude of the force, but we model the forces in tracker as their components fx and ay. So if this is the force, depending on the square of the velocity, the magnitude, how am I going to model the force as a vector? Well, one thing is that force is a vector, okay, and if magnitude is this, then this is the best way to write down first k times the magnitude of the velocity multiplied by the velocity vector. So if you just take the magnitude of force, you're gonna get this expression anyway. So this is it, and that means fx is going to be minus k times vx multiplied by the magnitude of the velocity, and minus k times vy fy is going to be magnitude of the velocity. Okay, so in that case, let's then verify that having these components will give us the velocity, sorry, the force magnitude like this. If we take just fx square, it's going to be k square, right? K square vx square times v. Fy square is k square vy square v, and if you add these two expressions and take the square root, we're going to get k times square root of fx square plus fy square, right? Square root of k square vx square plus vy square and v, right? And take the square root of this. So what we get is then k times square root to v, right? And well, square root vx square plus vy square is nothing but v, right? Magnitude of v. But in that case, what we have, oh, okay, we have square, just forgot to take the square of this. All right. So in that case, what we have is this, and then kv square can be taken outside the square root by k times v, and square root vx square plus vy square is again magnitude of v, so it is verified. This is k times v square. All right, so then the model or the components that should be written in the tracker, the components of the force, is going to be in this format, okay? And once we set this, we can just start what the real motion is. Let me first show what the real motion is to you. Let me run it. Okay, so let me erase this part. So okay, what you see over here is that one guy on the right is just shooting the badminton ball by just hitting it with the racket, and then there is other guy just doing nothing, holding the stick, saying that the stick is 1 meter, etc. So what you observe is that the motion of this ball, let me just get rid of this here. Motion of the ball seems that it's not a parabola, right? And that's because of the air friction. The air friction is just limiting the speed of the ball, and then it becomes like it just traverses a trajectory, like it's not going to be a parabola. Parabolas are the projectile motions, ideal projectile motions trajectories, just in the case that you ignore the air friction. But you see over here, it's very obvious that this real motion of this object is not a parabola, it's a projectile motion. So that's why, because there is this air friction. Okay, so let me run the tracker. I already had run the tracker. So what we see over here, let me first there is also this model, get rid of this model. Okay, what we see over here is that I just start the getting the position of the ball. Okay, let me run this frame by frame. The position of the ball, okay, at every frame, I just collected this position by using this tracker window. Anyway, by using this. Let me show it over here. Okay, by using a shift key and holding the shift key and then pressing the left mouse button at every frame by just clicking on the position of the object, it will get automatically tracker position in X and Y. What you see on the right is that all these position in X and Y. Okay, so Y versus time graph looks like a parabola, but X versus time graph is should be like a straight line, but what you see, in fact, it's not a straight line. It should be straight line because there is no any force acting on the horizontal direction for an ideal projectile motion. But since we have this frictional force, in our case it's going to be not a straight line. So X versus T graph is going to, the X motion is going to have some deceleration in the X direction. That's why we see a not a straight line, but rather it's kind of a curved graph. Okay, yeah. So after getting this position of the object at every point, that means that real position of the object at every frame, we just run the model, and what you see over here is that this is the model window. Probably you just see it. You're able to read because I just increased the fonts. Anyway, so I took just this mass information. It's 5 grams. 5 grams for a badminton ball. So I just found this in Google, in the internet. I put this mass, and it's typical mass. It might be a little different, but it's not a big deal because more or less the mass is going to be for badminton balls. More or less is going to be closer to this value. So the other thing is that G, which is 9.81, is theoretical value for the gravitational constant, and the other parameter is K. This is the coefficient of friction parameter. This KV square I told you, I just showed it. And this part is the initial values in time X, Y, and initial velocity and initial velocity in X and initial velocity in Y in terms of meter per second. But why do we have Vx is negative? Because the ball is going to the left, and the left direction is always negative. You can always take the negative X direction, so that's why X component is negative. Initially, so the object is just hit in the vertical direction, upward, so that's why we have a positive value over here. I put these values already beforehand just to cut the video short. Otherwise, I have to just figure out all these numbers by trial and tribulation. So I just put these values and just get rid of this axis. So and the next is you are going to type your model force over here, the x component is minus k times vx and square root of the magnitude of velocity, and the y component. In the y component, there is also this additional gravitational force, which is minus mg, and we put also minus k times vy square root of velocity's magnitude. So this is it. I mean, just I told you already that I've written down the force of friction as a model in the frictional motion. So this is the model, and the model I'm going to just make it visible. So what you see now is that the model's trajectory as a blue line over here, blue curve. The blue curve is the model's trajectory. Let me start from rest, from the first frame. If I run frame by frame, you see, if I put this model, force model like this, and with these initial values, and with this k parameter, which is 0.0071, what you see is that the model is more or less following the real position of the object in every frame, although there are some little differences you see over here. Overall, when I run it, okay, for example, over here it's kind of off the real object, but it's okay because it's on other frames, it's almost catching it. Well, not over here, but over here it's approaching the position of the real object, the model, and the motion completes right at this frame. Again, the difference between the model's position and the real object's position, there's some difference because our model is not perfect. But anyway, it's close, you see. And we can just analyze this on y versus t and x versus t graph by just also comparing these two models, okay, position versus time graphs. Let's also make this for x position. So what you see over here, these red dots and blue dots. Red dots are the real position of the object in y, and the blue dots are the position of our model, which is produced by this force model, right? Position y versus t graph. So, I mean, you see some discrepancies, of course. For example, let me enlarge this a little bit, make this smaller. So you see some discrepancies. Well, initially it goes like almost okay, but sorry, it's over here. Initially it goes like until the third, fourth data, it's okay. But after this fourth data, there is some discrepancies, and toward the end, it's again they are matching almost perfectly, somewhere, at least somewhere over here. So they end up, well, in x direction also we see more or less the model's position and the real position of the object more or less are matching. Of course, you can make this maybe better by using different k parameter. That I used over here is that 0.0071, and let's change it. What if there is any change? Let's change it to 7.5. So you see when I put 7.5, this y versus t and also x versus t, there are some discrepancies and very noticeable discrepancies in the matching. So, and if I make this again 1, you see it looks better, and also for x versus t graph it looks better. Maybe I played this, I played this, and then I get the best I can get is these graphs. Also, maybe you can play with the initial velocities, right? So when k is this value with these initial velocities, this is all you can get at best. But if I change also the maybe x and y velocities, initial velocities, well, it seems that x matching is better than y matching. Y matching is like kind of there is this mismatch over this part, a large part, almost half of the motion. Maybe we can decrease it to 784, 9.84. And running again. Not much difference. 8.1 maybe. Okay. So there is some difference. 8. Well, not much different, and this got worse over this part. Maybe now we can play with K. This is what, maybe 7 to 2. No, it's not getting better. It's not getting better. Maybe 7. Well, it looks okay now. Okay, so every time you get a new parameter k. Now next you play with the initial velocities. By playing with the initial velocities, if you can get better results, then you can improve further by again going for different k values. Going back and forth like this, you can reach maybe the best or almost the perfect results. This is all I can get, okay, with this model. So at least we can see that the model works, right? The model works because overall what you see, this red trajectory and the blue trajectory almost very close to each other at every frame. It is shown over here, right? So I mean, that's it. This is how you get. And the other thing is, of course, there is one thing more you can do, is that you just create a tape measure. What the tape measure is doing is that tape measure is just a tape, it's like a ruler put every frame, just measuring the difference between the model's position and the real object's position. So let me show its graph over here. Okay, this L, what you see over here in units of meters, what the tape measure shows at every frame. For example, at this frame, the difference, let me put over here. At this frame, for example, at this frame, like over here almost at top, it shows, the tape measure shows L is equal to 0.138. That means 13, almost 13, 14 centimeters. So the difference between the location of the real object and the model is 14 centimeters over here. But at the beginning and at the end of the motion, these differences are getting less and less. For example, over here, let's choose over here. Over here, for example, it's just 2 centimeters at this frame. And also you see on the right that where this happens. And for example, over here, the difference between the position of the model and the real object is like 3.5 centimeters. So these 3.5 and 2 centimeters are very good, but somewhere over here it's like 14 centimeters, is large. But you can always, what you do is, you can always, by playing with this, for example, let's make this, by playing with this, you can always change this tape measure graph. Superficially you can just overlook that whether, okay, this is getting smaller and smaller or not. For example, this is the highest mismatch is 14 centimeters and lowest one is like 2 centimeters somewhere over here. Well, let's see what happens when you make this, for example, very large number, like 79. Okay, so, but of course you have to run the video again. When this is 79, not much difference. All right. Okay, so you see, when you make 75, and the difference goes to like 45 centimeters, almost half of a meter. So it's a very bad model. Also you see this, you see this right on the real video. It goes quite okay until here, but after this point, like tab, the difference between the model and the object is very large, right, over these positions, okay? But of course, this is why because we deliberately just choose a very bad number for k. And let's make this again 71. Run it again. It's okay. Now, again, this L becomes plausible. Okay, so that means just for quantitatively, if you might want to just observe, or if you want to get an idea how successful is your model is quantitatively, this is what you can get. You can just run a tape measure, put this tape measure between the model and the position of the real object, and then observe it. How much difference, how many centimeter difference at every frame. Or the other thing is you can always go to analyze and just observe this mean value in x. For this parameter values, like k is 0.0071, the mean difference between the position of the object and the model is 8 centimeters. So when you play with this, you get a number over here, a mean number. If this number is getting smaller, then your success is getting higher, okay? Because this is the difference between the position of the model and the real object. Smaller this number, better the success of your model is, okay? All right, so, I mean, this is a quantitative measure that you can always do. And of course, this is, you should do if you just want to measure your success of your model. This is it. I mean, just run the tape measure and analyze the tape measure in statistical window, and you just look at the mean difference between the position of the object and the model. So this is the quantitative measure of your model success, okay? All right, that's it. So this is it for two-dimensional air friction model. By using tracker, you just saw that we model a real motion of a real object like a badminton ball, and we produce a nice model, we can say.